All right, today we're going to talk about balancing chemical equations. And to start you out thinking about this, I'd like you to think of an analogy of a teacher taking roll during a fire drill. So she has her students in the classroom, she knows who's there today, and the fire alarm rings. So they all file outside. And anyone who's ever taught before knows that kids do not stay in the formation that you expect them to. So likelihood is the kids are going to walk together with their friends, even if they're being totally silent, and they're going to move around and get in a different order than they were sitting in the classroom. And so when they get out to the field, the teacher needs to take roll again, and she needs to make sure that she's accounting for every single student who was there before again. Now, this is like a chemical equation. Matter cannot be created or destroyed. So you need to make sure in a chemical equation that you have the same number of atoms on both sides of the equation, even if they're in a different arrangement or a different formation. So I love camping, and I thought this would be a nice analogy for this. So if you've ever eaten s'mores, then you can imagine this. 2 graham crackers, which we're going to use the chemical symbol of capital G lowercase c, 1 marshmallow, and 3 chocolate squares are the ingredients that you need to make a s'more. So imagine that this is chemistry. Can you write the equation for making a s'more? And what would be the chemical formula for the product or the s'more? So go ahead and write that in your notebook. So you should have 2 graham crackers, 1 marshmallow, and 3 chocolate squares. And I'd like to point out that there's an invisible 1 right here. We don't really use ones in chemistry. And these 3 pieces yield this, we're going to call this the compound or the s'more itself, which is GC2MMCS3. Now, if you set up a little table where you have your reactants and your products and you count out each ingredient, you have 2 graham crackers, 1 marshmallow, and 3 chocolate squares on the left side of the equation. And now on the right side of the equation, you have 2 graham crackers, 1 marshmallow, and 3 chocolate squares. And so this is now a balanced equation. And if this were chemistry, this is what you're seeking. You're trying to get the equation to balance and have the same number of atoms on both sides. Now notice it's like the fire drill. The kids were here and then they rearranged themselves and now they're over here in a different formation, but everyone's accounted for. Now, how would your equation change if you needed to make 4 s'mores? So you're sitting around the campfire with your friends and you need to make 4 s'mores. So go ahead and change your equation so you get 4 s'mores as your product. Okay, so what you should have are your coefficients from before multiplied by 4, because you need 4 over here. And if you count the atoms on each side, because you have 4 times 2 graham crackers on the right, you need 4 times 2 or 8 graham crackers on the left. So you need your 2 to become an 8, or in other words, multiply by 4. You have, now remember, this 4 gets carried over to each type of atom in the formula. So there are actually 4 times an invisible 1, or 4 marshmallows on the right. So you need 4 marshmallows on the left. And there are 4 times 3, or 12 chocolate squares on the right. So you need 12 on the left. And this is now a balanced equation. So here's another analogy. A skateboard is made with 4 wheels, 2 trucks, and 1 deck. And you're going to use these chemical symbols for those 3 items. Can you write the equation for making a skateboard? And what would be the chemical formula for the final product, which is your skateboard? Now you should have, to make one skateboard, you should have 4 wheels, 2 trucks, and 1 deck. And so on the right-hand side, you should have made your molecular compounds containing the same number of each type of atom. So if we set up this table again, we indeed have 4 and 4 wheels, 2 and 2 trucks, and 1 and 1 deck. And this is a balanced equation. Now, if you imagine you work at a skateboard shop and you have a customer come in and they ask you for 5 skateboards for an order. Now, how can you manipulate your equation? And you're really just doing math, but we're talking about chemistry here. How can you manipulate your equation to make 5 skateboards for your customer? Go ahead and do that in your notebook. So you should have, in order to make the 5 skateboards as the product, you need 20 wheels, 10 trucks, and 5 decks. Okay, and all I did here was I multiplied at each coefficient in the original equation by 5. So now we have this balanced number on each side of the equation, and this is a balanced chemical equation. Now if we apply this to real chemistry, here is the equation. We call this a skeletal equation when it's not balanced. That's why there's a skeleton here. For H2O, which you should recognize as the water molecule. So if we have hydrogen gas and we add oxygen gas, we get water, as long as we have enough energy there. If you set up the little table, you have 2 hydrogens and 2 hydrogens as your reactants and products. You have 2 oxygens, but you only have 1 oxygen as a product here because you just have this invisible 1. So unfortunately, this is not balanced. So what can you do here to balance this equation and get your numbers to work? What you can do is you can plop a 2 as a coefficient in front of your hydrogen gas and a 2 as a coefficient in front of your water molecule. Now you might be saying, are you allowed to do that? Well, yes, because you have 2 molecules of hydrogen gas. So you could add a 2, you could add a 3, a 4. It just means that that's how many of that molecule you have. And you, at the end, have 2 molecules of water. And so if you set up the table, you now have 4 hydrogens and 2 oxygens as your reactants. And you have 4 hydrogens, and this 2 gets applied to here, this oxygen, 2 oxygens as your products. And this is a balanced equation. So we're going to be practicing this more with some activities, but I wanted to just point out to you, if you haven't noticed, haven't picked up on this yet, that you can only insert coefficients in front of a chemical species. It is absolutely wrong to ever change the formula of a chemical species, meaning you cannot change a subscript because, as I showed you here, water is water, H2O. I cannot just put a 3, H3O. That's a totally different chemical. But I can add a 2 and make it 2 water molecules. So keep that in mind as we go ahead with the next activities.